All right, everybody. I have to actually start on this question that we finished on in class because I messed it up, and thankfully, one of your very astute classmates caught me because I forgot we have this orange point up here, that f of -2 equaling 1, and I need to have that being part of my graph. And right now, I have an equation that's actually not a function. I fail the vertical line test right there because my graph touches at two places. This is why over here, we need to have that open circle in our filled in circle because that vertical line goes right through that open circle and just hits the filled in circle. So there's a couple of ways that we can repair this. We can either take this part right here and draw an open circle there at -2, so that fixes it. Or I could take this graph, continue it up here, hit that, come back down, and it can be pretty steep, and then go off to infinity. So either one of those options really would be fine to fix that. All right, let's take a look at the next one here. So again, hopefully you've tried this one out on your own, and then you can compare your graph to what I get here. So with one like this, where I've got a lot of conditions written out, I still do want to start like, oh, sweet, it gave me a point. So let's do that first, right? So maybe we'll do it bigger this time so I don't miss it. There we go. So it's got to go through 2, 0. So that is a point that has to be on our graph. And so that's our number one thing. Then taking a look at up here, that tells us that our first derivative is positive, so our function's going to be increasing. And then our second derivative is negative, so that tells us that we're concave down. So our graph is going to have to look something kind of like that for this part of our graph, so from -infinity to 0. Then this second part here says that our first derivative is negative, which means we're decreasing. It's been a little while since we've looked at these. And the second derivative is positive, so that means we're concave up. And so from 0 to infinity, our graph has to do something like, I also have a hard time drawing this one. To do that, you have to really think about what decreasing and concave up looks like. A good sort of one to think about is e to the -x. That's decreasing and concave up. So now we're given another sort of interesting situation here that we've got to be continuous at x equals 0. So that means that from the right and the left, we have to get to the same place. Our graph has to be connected there. So our graph is connected at x equals 0. We don't have an open circle there or anything like that. It's just we've got to be able to draw that part without lifting our pencil, but we're not differentiable there. So our graph is going to have to do, so there's kind of basically three ways that we can be not differentiable, right? We can be not defined there, so we could have an open circle, or we could have an asymptote there. So I'm just going to try to draw it kind of like this. If we have an asymptote, we're not differentiable, so a place where we're undefined. We don't have that case. Also another case could be, piecewise function where it's got, those two bits and there's a gap there. All of those places are places where we're not differentiable. We don't have those cases here because we were told up in that previous thing that we are continuous there. So our graph is connected. So our graph's going to have to do something like that or a corner. It's got to be one of those corners or nodes, one of those pointy parts on our graph where we're getting the slope from one side is different than the slope from the other. And if you actually look at our blue graph and our green graph and we put those together and kind of draw like that, so increasing and concave down, and then decreasing and concave up here, making sure we go through that point that's on our graph, we made it so that we have a node there. So I can draw that whole graph without lifting my pencil, but we're not differentiable at 0. And where I position this point, that output or the y value at 0, that really doesn't matter because that's not something that they gave us on the list that we had to, make sure that it was at a certain place. That's why I didn't like put it at a specific spot on the grid because it doesn't really matter where that is. It can be anywhere that we want. The only point that we have to have is that one big purple one that I made there. All right, let's take a look at the next one. So here we have the graph of f prime of x. So This is our derivative. And we want to draw a possible graph of our function f. So really, we don't know the exact position of where f is going to fit on our graph here, but the first derivative can tell us things about our graph. That any place where our derivative is above the x-axis, so any place that we have red there, our original function is increasing. We can say that's because f prime of x is positive. So positive meaning we're getting positive y values. Any part that's below the x-axis, so this part right here, that, oops, I wanted to do that still. This f is decreasing, and that's because our derivative is negative. So some other points that we kind of have of interest on here, like right here at 1 and at 3 and at 6, or -1. So -1, 3, and 6, those are critical points because those are places that f prime is equal to 0. And let me write that as f prime of x. Make that look a little better. Now, only 2 of them are actual mins and maxes. At -1, we're increasing before that and then decreasing after. So we are going to have a max there, right? Because we're increasing and then we're decreasing. And at 3, we're decreasing before and then we're increasing after. So this is, oops, I don't want to write it on the graph. So this is it's still the eraser. This is a min. See, it's not even any better when I just try to make you a video. At 6, we're increasing before, we're increasing after. So at 6, this is just going to be a place where we kind of flatten out, but we still continue to increase. So actually, kind of drawing these little bits that I've drawn here in purple, that's kind of what our graph's gonna look like. So, and other points that we have that are of interest, and I don't know what these points are exactly because they're not very well marked here, they're not exact points, is any place where we have mins and maxes on our derivative, those are places where we change concavity. So we change concavity there. Again, that's concavity change. So these are points of inflection, concavity changes. So that's going to help us maybe draw an okay picture here. So let's see, we're going to be, let's see, our positive there, and then we go to decreasing there. I'm sort of thinking about what's happening, how the rate of change of the first derivative is. If your concavity is not perfect on this one, that's totally okay. But I'm going to draw a max right there, and I'll kind of do something like that. And then it's going to go like this, and then maybe we'll have our minimum there. Oops, let's connect that a little bit better. And then here at 6, it's going to have that point where it levels off and it's going to go back up. Okay, not too bad, not too bad. It's not the most beautiful looking picture, and the picture that I have on my notes is a little bit different, and your picture might be a little bit different here as well. But the thing that we want to make sure is that places where we're increasing, we're actually increasing. Places where we know we're decreasing, we should be decreasing. And places where we know we have mins and maxes, we should also have mins and maxes. All right, let's look at the last one here. So we've got a population that's changing over time, and it grows at an increasing rate for the first 6 months, or first 3 months. So it's telling us from 0 to 3, increasing rate. So what that's telling us, because it's an increasing rate, so our rate of change is increasing. So it's really actually telling us that we're concave up. So that rate of change is increasing as we're going. And then it continues to grow, but at a decreasing rate for the next 3 months. So from 0 to 6 months, it's growing at a decreasing rate. So that's telling us we're still increasing, but now we're concave down. So we're growing, just not as fast. Then it says at the 6 month mark, the population remained constant for 3 months. Okay, so for 6 to 9 months, it's constant. So it's flat. Okay, we got that. But then it increases at a constant rate for the next 3 months. So from 9 to 12, it's increasing at a constant rate. Things that increase at a constant rate are linear, right? So that rate of change is always the same on that straight line. So increasing at a constant rate is going to tell us that we're linear. And then finally, over the course of the second year, 12 months, right? So 12 to 24 months, the population dies off with a relatively large negative growth rate at the beginning of the second year, gradually reducing in magnitude, which just means it's getting smaller and smaller. Might be still be negative, but it's getting smaller, to a relatively slow negative growth rate by the end of the second year. So this is telling us that we have a rapid decline, then slowing down. So drawing these sort of little bits of graph here, we can actually put these together and make these graphs. This is what all of the little bits should look like. So if we go over to the next slide and take all of our 5 pieces and put those together, our graph is going to look like this, that we're going to have, we had some sort of initial population here. There's a reason why I didn't put a y-axis on here because it kind of doesn't matter. But we're increasing at an increasing rate, and then we're still increasing, but at a decreasing rate. So it's that concavity. We change concavity there. Then we're constant for 3 months. Then for 3 more months, we have a constant growth rate. So we've got that linear part. And then for the last few months there, the last year, it starts a steep decline and then it starts to level off. So that's what our graph should look like.